Building design is a complicated operation that includes architecture, engineering, art, and technique. Generally, the climate is a very important factor in design. Shapes, orientation, and size of the building are defined by the region's climate. When the building takes in consideration the weather conditions with the aim of reaching indoor and outdoor comfort with minimum dependence on mechanical systems for cooling, lighting, and heating, it's called passive design. In the current project, passive design strategies will be investigated and implemented to design a country house in a temperate climate location in Europe. The aim of this project is to define a location in temperate climate country in Europe. Design a country house with given requirements and minimum building code standards. Investigate different strategies of passive design. Implement them to enhance the country house design. Then assess the building design to evaluate the effectiveness of passive design strategies using the software IESVE. The project site is in Spain, more exactly in Algeciras, which is located to the west of the Passage of Gibraltar. It is known with its strategic international port that made from it an important economic hub in Europe. Algeciras is also known with its green environment and touristic places. The site is on elevation of 200 meters from the sea level. It is easily accessible through the town circulation net. With hot and dry summer and cold and rainy winter, the maximum temperature degree reached in Algeciras doesn't touch 28 degrees during July and August, while the minimum temperature degree is not less than 10 during January. The south of Spain receives two different winds. The warm and humid Levant wind blowing strongly from the eastern region and the Ponent wind from the west and northwest with thermal effect in summer for climate refreshment. The site is well exposed to the sun radiation from the east and south. However, the mountains provide shade from the west region. The design brief requires a country house for a large family containing one main house building and a separate guest room building. It will include 2 or 3 stories with 4 rooms, 4 washrooms, a large farm, fences, and a sun space will be included in the guest house later. The first stage in the design operation is to define the unit of the design, which is composed of 2 units, the static unit of 4 by 4 meter for rest areas and the circulation unit of 2 meter width. This makes a total design unit of 6 by 6 meters. Then the design unit is duplicated in 2 directions to provide a space that should be enough for the project space requirements. Finally, the different project spaces were distributed to achieve the design brief requirements. The country house includes 2 stories and contains a salon space, 4 master rooms, 1 office space, and the guest room with 1 level. The architectural style of the project matches the existing Mediterranean style with red roof and white buildings. It was concluded that a significant time of the year is characterized by cold climate compared to the hot climate which covers around 3 months of the year. As a result, the passive design strategies will be focused on passive heating more than passive cooling. However, the ideal is to apply a passive design strategy that works for cooling during summer and heating during winter. Different passive heating and cooling strategies were investigated to be implemented in the project design, such as south building orientation, direct gain using thermal mass material and south-oriented glazing, indirect gain such as trombe wall, sun space, shading devices, and landscaping. Passive House is an international low-energy building design standard. It aims to provide a good indoor air quality, thermal comfort, and low energy consumption design. To achieve these goals, Passive House considers the indoor temperature, flow rate per person, and the volumetric capacity of the system. The ISVE software was used to assess the passive heating and cooling strategies that was implemented. By simulating the initial design building first, then evaluating each strategy and its effect on heating and cooling energy loads. The first stage was the setting of the base case building construction and the current orientation of the project. An initial evaluation of energy consumption was applied by simulating total energy consumption of the building in 3 cases. The first case was with both heating and cooling system operational. The second case was with only heating system operational. The third case was with only cooling system operational. And the results show that most of the building energy goes to the heating loads. It was observed that turning off cooling system doesn't affect the comfort zone of the building during summer. However, turning off the heating system makes the comfort zone unachievable during winter. The first strategy was assessing different building orientations to identify the most efficient orientation regarding energy consumption. The north orientation of 90 degrees showed the maximum efficiency of energy, with around 100% decrease. Using Suncast analysis and weather data in IES, 3 dates were selected for simulation. August 12 as the hottest day in the year, December 29 as the coolest day in the year, and April 12. The first simulation indicates the significant amount of energy consumption during winter compared to summer and spring. This is due to the heating loads needed to ensure thermal comfort in indoor building. The second strategy was the building airtightness from passive house regulation. It aims to ensure maximum insulation of the building envelope by limiting the U value to 0.15 maximum. This was done through multi-layers of material separated by cavity to increase the insulation. The simulation results showed a significant reduction in energy consumption from a total of 118 MWh to 70 MWh. A saving of 41% of heating loads was achieved with this strategy. Comparing different scenarios, we remark that consumption was decreased in cold seasons, winter and spring. The third strategy was to increase the direct heat gain through south-oriented windows. The Suncast analysis allowed to identify the building facades receiving maximum of solar radiation during winter. The IS configuration was based on high thermal mass materials for the construction profile, ensuring the U value criteria, and the increase of south glazing surface. Significant decrease in energy consumption was observed as the amount decreased from 70 MWh to 65 MWh. The enhancement was achieved mostly during the spring as it provides a significant amount of solar radiation, while winter is generally cloudy. South-oriented window strategy decreased energy loads with around 7%. The season scenario shows that even in summer, direct solar heat decreases the energy consumption. The shading device strategy was proposed to decrease solar radiation provided by the big south-oriented windows in summer. The Suncast analysis shows that the shading devices minimize solar radiation on facades. However, the simulation results indicate that the enhancement is achieved only in summer with low percentage and has a negative impact during spring. The sun-space strategy was implemented as an open-wall, direct gain, connective airflow, and thermal storage wall. The simulation results show that the sun-space strategy was slightly efficient only during spring due to the significant solar radiation and the orientation of the sun-space itself. After evaluating different strategies, the simulation results showed that the most efficient strategy was the building airtightness because of insulation layers that minimize thermal bridges. Solar heat gain was efficient with less percentage. The building orientation affected the energy consumption positively. However, the shading devices and the sun space didn't show an interesting enhancement. A total energy saving of 46% was achieved. A macro flow study was applied to design an efficient natural ventilation during summer. The analysis showed that the summer wind comes from the east. All windows were set with 20% openable areas. The simulation showed that the airflow is significant from the indoor to the outdoor in the south facade and the glazed roof. However, the ideal scenario is to design an airflow from the east to the west to ensure a good ventilation of the building and a comfortable indoor quality. As solution, all the south glazing and the skylight was set as non-openable. 20% of glazing was open on the east and west facades to ensure a comfortable airflow. The microflow opening profile was set depending on indoor temperature and CO2 concentration level. The results show that the glazing opening of 20% with orientation east-west can give a comfortable air temperature of 22 degrees and air velocity between 0.1 and 0.3 meter per second, with a comfort zone better than mechanical system. The current project shows the implementation of different passive design strategies to design a country house in Algeciras in Spain. The IES software simulation indicates the high efficiency of different strategies such as building orientation, air tightness, and direct heat gain, while other strategies was not interesting for Algeciras region and the building design itself.